Greetings everyone and welcome back to some more complex analysis. Today we're going to be taking a look at this integral from 0 to pi of log sine of x dx. That's a pretty cool integral in my opinion. Let's get rid of this chair here. So how exactly do we evaluate this, or I guess how do we usually evaluate this? I believe people just use symmetry all the time. So they rewrite that in terms of cosine or something like that, and then they combine the integrals together. I think then you get sine of 2x or something, and then they do some other symmetry things and they get some answer at the end. That's pretty boring in my opinion because you're done in like, I don't know, 5 lines or so. We're going to be using complex analysis today, of course, and that's going to make this guy a lot more spicy. So how exactly do we get started with this? Well, first of all, we need a complex function to integrate. I don't know if you can come with a nice function for this. I guess what we'll usually use is just the function itself. So f of z is equal to just the integrand, so log of sine of x, but instead of x we have z over here. So that's our function. Now this is an okay function to use. The only problem is it has the sine in there, which isn't really too nice in the complex plane. Usually if you work in complex plane, you like to use exponential functions. Luckily though, we can rewrite sine in terms of its exponential function. So how do we do that? Well, first of all, this is equal to the logarithm of, sine. What is sine? It's exactly e to the I times z minus e to the minus I times z, all divided by 2i, like so. That's the sine function. And now what we can do is we can rewrite this guy a little bit more. We can rewrite this as, let's say we have the logarithm of e to the iz. And I'm going to do, we'll do that in the next step actually. We might as well do it now. I'm going to factor out e to the minus iz everywhere, just so we get one exponential factor, and you'll see what I mean by that later. So I'm going to factor out e to the minus iz to the back, so e to the minus I times z, and at the front we're going to be left with e to the 2 times I times z, and then we have a negative 1. So you can check for yourself that this works here for the logarithm, because if you multiply this back in, that's e to the iz, and then minus e to the minus iz, that's exactly what we have. And what I'm also going to do is I'm going to split off this 2i, so that's going to be negative. We have the logarithm of 2i. Now, if you forgot how to calculate log of complex numbers, here it is up over here. So if you have the logarithm of 2i, that's just going to be equal to, we have the logarithm of absolute value of modulus of the 2i, and then we have plus I times the arguments of the 2i. Okay, now what is log absolute value of 2i? Well, absolute value of 2i, that's just 2, so that's just going to be the logarithm of 2 there. And then plus I, what is the argument of 2i? Well, we need to make a choice for what arguments we're going to be using as well. Let's just use the standard one, so from minus pi to pi, or 0 to 2 pi. I don't think it really matters in this example here, but let's just do minus pi to pi. I think that's the usual one that people use. So the argument of 2i, well, that's up over here, so that's going to be exactly pi, but then we divide by 2, like so. So in fact, this guy, log of 2 plus I, pi over 2, that's exactly logarithm of 2i. So we can plug this in over here. So this is going to give us a minus the logarithm of, that's going to be 2. And because we subtract, we're going to have minus, and then we have I times pi over 2, like so. Okay, so this is what we're working with. And finally over here, we can split off this guy as well. So we can split the log once again. So this is going to give us the logarithm of, we have e to the 2iz minus 1. And then we have a minus the logarithm of e to the iz, like so. Okay, now in fact, this is going to reproduce I times z. Not all the time though. This highly depends on what value of z you put in. But for our purposes, I might discuss this right now. We can put I times z there, and we're just going to have minus logarithm of 2 minus I times pi over 2. So if that wasn't clear, the log and the e cancel. That leaves us with the minus iz here. Now, why on earth does this work out nicely here? For that, I need to draw out the complex plane and the rough contour that we're going to be using as well. So let's do it on this side over here. What we're going to be doing is we want to integrate from 0 to pi. So here's our complex plane. Here's the real axis, so real of z, and then we have im of z up over here as well. What we're going to be doing, we're going to integrate from 0 to pi, so that looks something like, we go from 0 to pi, of course. Before we just draw that line, we do need to realize that at 0 and at pi, there's going to be some issues, and I need some blue chalk here. Oh, I dropped some on the floor here. So in fact, at 0 and pi, we're going to have branch points because, of course, if you plug 0 and pi into that sine function, you're going to get log of 0, which ain't good. So we're going to have branch points at 0 and branch points at a pi over here. Now, we're not going to worry about the arguments too much in this video. I'm pretty sure if you just use the standard principal arguments, these guys are going to be oriented outwards. So they won't really interfere with our contour integration in any way. Maybe some of you guys can confirm that for me because I'm not actually too sure how you could get these from the log. It's a bit of a weird function to find branch cuts and branch points. But yeah, maybe one of you guys can tell me in the comments. So we want to go from 0 to pi. We can't quite do that. We have branch points. Let's start some distance epsilon away. So we're going to start at epsilon, and we're going to end at pi minus epsilon right over here. So that's going to give us a little bit of room, so we're not integrating on the branch points. So this is the part that we want to integrate, and let's call this guy over here omega. That's the path we'll call. So this is the part that we really want to get, and how do we complete the contour from here? We want to use contour integration. Well, you can't really go to the right or to the left because you're going to have branch cuts and it's just not nice. So if you can't go sideways to complete your contour, we could do a little semicircle, but then you need your two sides to go out to infinity. If you can't go sideways, then just go upwards, I guess. So we're going to be doing a little bit of a rectangular contour today. I've done a few of these before on the channel. So we're going to go upwards. Before we do that, we need some little circles, or quarter circles, just to avoid the branch cuts or the branch points. We're going to go upwards like so. And then to complete the contour, we're just going to put a line across over here. So we'll call this line up here, let's just do gamma, and then we'll call this path psi 1, and then we have psi 2, and we're going to go anti-clockwise in the positive direction. And we'll call the little paths here little gamma 1 and then little gamma 2, like so. And we'll call the whole entire contour, let's just call it C, why not? Okay. Now, you notice one thing with this contour here, which makes it really quite nice. Everywhere that we're going to be integrating, so observation here, we have that the real part of z is, well, that's on the interval minus 0 to pi. So the real part of z is always kind of bounded in that range. And that's exactly the reason why we can cancel the log and the exponential there. It's because if you kind of rewrite this exponential a little bit over here, let's do it right now. So if you rewrite the exponential, you'll notice that e to the minus I times z is equal to e to the minus I times x, let's say. And then you have e to the minus I times y, where y is the imaginary part. But that's going to cancel, leaving us with e to the y like so. So x over here, this is the real part. This is a real number here. So if you try to apply logarithm to this, well, you have e to the y. That doesn't really cause too much trouble. You can always invert it because with log and e, they're perfect inverses when y is a real number. However, the trouble comes with this x here because it's also multiplied into that I. So in the complex plane, log and e aren't always inverses. So I might make a video on this in the future because I can go into quite a bit of detail. But essentially, in the complex plane, the range of the logarithm looks like these strips over here of heights. That's going to be 2 pi. So these strips of heights 2 pi. So this is the range of the logarithm. And the thing is, if you have some number, complex number, let's say over here in the complex plane, and he exponentiates this guy, well, you might get to, let's say, e to the z here somewhere, but then when you take the logarithm of this guy, it's always going to map back over to here. So in fact, you're always going to be at an offset of some integer multiple of 2 pi in the imaginary direction. So that happens with all the complex numbers that are outside of this strip. When you exponentiate and then map back using the logarithm, you're always going to enter back up the strip and not in the original position you started. With the exception, if you started in the strip, then if you map out with the exponential, then map back with the logarithm, well, you're going to end up back over here, which is perfect for our purposes. You'll notice that x, that's the real part, right? But x equals real part is always on the interval 0 to pi. And if we choose the principal argument, then our logarithm will always map back into this shaded region, which means that as long x is on the interval negative pi to pi, we're going to start somewhere in the strip. If you exponentiate, then map back into with the logarithm, then the log and the exponential are perfect inverses, which is exactly why we could cancel the log and the e over here. Now, if we did another contour integral, let's say it was out over here somewhere, then x would be greater than pi, which means you would probably start up above here, above this vertical strip. So I think you would need an extra addition plus 2 pi I or something there. But again, that depends on how you choose the principal argument. So I might do another video on logarithms because it is rather interesting, but yeah, that's just to convince you that you can cancel those two inverses there. So the next thing we'll do is we're going to write out some of our integrals. So we have the integral. I think I might do it over on this side here, and I'll leave the bottom here for our parameterizations. First of all, the integral over c. What exactly is that going to be? Well, there's no poles in there or anything, so the integral over c, that's just going to be exactly equal to 0. So we have 0 being equal to the contour integral over c. But what is that? That's going to be the integrals over all these parts here. So we have the integral over omega plus the integral over gamma 1 plus the integral over gamma 2 plus the integral over psi 1 and then plus the integral over psi 2 and then plus the integral over gamma. So there's a lot of integrals here for us to evaluate. Luckily, though, they're not too bad to do, I don't think. So we might as well get started with, let's say, the integral over omega. The integral over omega, that runs from epsilon to pi minus epsilon. And what I'm going to do on the second row, I'm going to put the results in the limit as epsilon approaches 0. And I need to give the height a parameterization as well. Let's say this point over here, this is pi plus I times n. And this point over here, this is 0 and then plus in, so this is basically I times n pretty much. So this was the 0 here before, this is the pi, which are, so I should have done this in blue, this is our branch points. And there's a helicopter, I don't know if you can hear that, which is a bit annoying, so hopefully that goes away soon. So we have limits as epsilon goes to 0 and limits as n approaches infinity as well, because the idea is we're going to take this path up over here, and we're just going to make it keep going up forever, and it's not going to stop. It's going to go to infinity. So, in the limit, the integral over omega, that's just going to reproduce our I that we started off with over here. So let's let I be equal to this guy. So this is going to just reproduce I exactly. Okay. Now let's take a look at the integrals over gamma 1 and gamma 2. These are integrals around our branch points here. So they're actually going to vanish as we take the limits. And I might leave that till the end of the video because doing those integrals are rather boring in my opinion. So I'll leave that to the end. Let's take a look at the integral over psi 1 and psi 2 over here. These two are going to be rather interesting in my opinion. The psi integrals are always interesting. So usually it actually works out pretty nicely if you do the integral over psi 1 and psi 2 together. So if you have two vertical paths in the complex plane, do them together, it probably works out nicely most of the time anyways. So let's see over here, we have the integral over psi 1 and then plus the integral over psi 2. So how are we going to parameterize psi 1 and psi 2? Let's go back over here. So psi 1, we'll notice that every z on there can be written as, well, that's just going to be I times t, because it's just on the imaginary axis, so you have I times t, but t is going to go from, that's going to be n back to epsilon back over here. So we have t going from n to epsilon, and yeah, dz is just going to be I dt. So let's write that down, dz equals I times dt. and then how that side 2, or every z on there, or the real part, that is going to be exactly pi, and we're varying our imaginary part, so we have plus I times t here, and a t this time is going to go from epsilon up to n like so, and dz, once again, that is going to be I times dt. So those are our parameterizations there. Let's plug that into our integral. So first of all, what do we have? We're going to use this form of our function f of z that we derived at the start of the video. So let's see what we get here. We have the integral, psi 1, that goes from n back to epsilon, so n to epsilon of, we have the logarithm of e to the 2 times iz. But what exactly is z? Z is just I times t. So if you plug that in, you're actually going to get minus 2t, because I times I is exactly negative, I believe. So that should be right. And then we have minus 1. And then we're going to get negative. I'm going to write the constants first. So we're going to get log of 2 minus I times pi over 2, and then I'm going to write the negative I times z next. That's going to be negative I. What is z? Z is just going to be, well, that's just going to be I times t, like so. And that should be it. And we're going to finish off with an I dt. So all of this, that's going to be multiplied by I times dt. Now, I'm going to put the integral over psi 2 underneath, and you'll see why in just a sec. So we're going to have plus the integral psi 2, that's going from epsilon up to n. Okay, so this is going to be integral from epsilon to n. We have the logarithm. Okay, if we plug a pi plus I times t into our function there, what exactly are we going to get? Let's just do it in this little corner here, because I just want to plug it straight in. So we have e to the 2 times I, t, or z, that's going to be pi plus it. So we have pi and then plus it. And you'll notice one thing, we can rewrite this as e to the 2 pi I, and then e to the minus 2t, because you can just expand out that bracket and then split up the exponential. But then e to the 2 pi I, that's exactly equal to 1. Okay, so this is equal to e to the minus 2t, which is rather quite nice, because we just get back what we had there. So e to the 2t, and then we have negative 1. Okay, and then we have minus the same constant, so log of 2 minus I pi over 2, and then we have minus I. Okay, z goes in here, but z on side 2 is exactly pi plus it. So we have, I guess I'll just write it first, and then plus pi, like so. Okay, end of bracket, and then we have I times dt. All right, now, you'll notice there's a lot of things in common, which is really nice when you have this. Furthermore, the bounds are reversed, so let's get them in the right order. For example, with this one over here, let's reverse this guy. So this guy now runs from epsilon to n. And because the bounds are the same, you can combine these two integrands together. And because there's a negative over here, let's take a look at what happens. You have something and then minus something. So this cancels, and then these two are the same, so these cancel, and then these cancel as well, because they're the same. And then this it and this it cancel, because those are the same, and you're just subtracting, and you're just left with this extra pi, which survives at the end, which is really quite nice. So overall, what do we have? We have the integral. That's an ugly integral. So we have the integral from epsilon to n. What do we have? Well, everything in this integral, that's gone. We're just left with integral from epsilon to n. We have negative I times pi. Okay. And then we have an extra I here as well. So negative I times I, what exactly is that? That's just 1, I believe. So let's make sure our arithmetic is right here. So negative I pi times I, that's exactly pi. And then we have a dt. So if you integrate this guy, that's really quite easy. That's just going to be equal to pi, and then we have n, and then minus pi times epsilon. So that's going to be the result of the integral over psi 1 plus psi 2. And then you may be screaming a little bit, because there's a very big problem. First of all, epsilon is going to go to 0, so fine, this guy's going to be 0. But then n is going to approach infinity. We have a pi times n over here, so are we saying that the integral over psi 1 and psi 2, that's going to approach infinity? That's no good, is it? And yeah, I was kind of concerned about this, and I actually stopped doing this problem when I saw this come up. I was like, nah, I probably did something wrong. Let's just do another problem because it can't be stuffed anymore. But then, yeah, I was thinking, well, I haven't even evaluated the integral over gamma yet. Maybe this could save us, and it actually will. This will produce something that will cancel that pi epsilon or the pi n we had over there, and everything will be nice and, yeah, nice and finite. So let's do the integral over gamma next, and we'll see what this will evaluate to. So I guess we'll just do the integral over gamma over here. So let's write down to parameterization for our gamma integral. So gamma, how is that going to work out? Well, first of all, what's varying? It's the real parts. The imaginary part is fixed at I times n. So we have z is equal to, the real part is going to be, let's say, t, and then we have plus I times n. So t, that's going to go backwards, so we're going to go from pi back to 0. So yeah, t on the interval pi to 0, using the illegal notation once again, and then we have d, well, that's dz. What is that going to be? That is going to be equal to dt. That's pretty simple. So let's plug that in and let's see what we get. So first of all, integral over gamma. That's going to be equal to the integral. We're going to go from pi back to 0 of, what do we have? We're going to plug t plus I times n in everywhere. So first of all, we have the logarithm, which is still there. We have log of e to the 2i. What is z? Z is going to be pi, or t plus in actually. So we have t and then plus in. Okay, and then we have a -1. And then we have minus, let's put the constants next, so actually it doesn't matter in this case. We have minus I times z. Z is exactly t plus in. Okay, and then we have minus the logarithm of 2, and then minus I times pi over 2. All right, and then what else do we have? We have the differential, which is dt, and I believe that should be all we need to plug in. Hopefully that is right. So first of all, we have, yeah, we can split up this guy, I guess. So what is that going to be? We have negative out the front, integral from 0 to pi. We have the logarithm of, let's expand out this guy here, that's e to the 2 times I times t. And then negative, so I and I, that's -1. So we have e to the negative 2n like so. And this is rather nice because n is going to infinity. We have e to the negative 2n, so that's going to be 0 actually. We have a -1 and then minus I times t. Negative I, positive I, that's exactly 1. So that's going to be plus, plus n. And then we have minus the constants over there, so minus log of 2, and then minus I times pi over 2 dt. Okay, so next up, what can we do? We can assume that we can bring the limits inside of the integrals, and if we do that, this n, that's going to disappear in the limits. So how should I write this? I guess let's first of all split up the integrals. So in the limit, as n approaches infinity, what is this going to be? Well, that's going to be equal to negative. We have the integral from 0 to pi. We have the logarithm of e to the 2 times I. Actually, that's going to be 0, isn't it? That's 0 because n's are going to go to infinity. This guy's going to be 0. So we're going to be left with log of -1. What is log of -1? Let's put it over here somewhere. Log of -1, that's going to be equal to, we said it before, it was the logarithm of the absolute value of -1, and then plus I times the argument of -1. Okay. Log of absolute value of -1, well, that's log of 1, which is a 0. And then we have plus I times argument of -1. We're on the principal argument, that's going to be pi. So we have plus, yeah, that's going to be plus I times pi, like so. Okay, so we're going to have I times pi there instead of this logarithm guy. So we have I times pi dt. And then we can just integrate all these guys over here, which isn't too tricky to do. First of all, we have, if you distribute this negative into here, that's going to become a plus, actually. We have I. If you integrate t, you're going to get t squared over 2. If you plug 0 into pi, and that leaves you overall with a pi on 2. You can check that for yourself. And then we have a plus n. But actually, we have this negative we need to bring in. So this is going to be a -n. negative n, that's a constant, so you just multiply by the length of the interval, which is pi. And minus n pi, that's exactly what we're after, because, did I put it in the blackboard above? We have a positive n pi over here, which was causing trouble. So that's going to completely cancel, which is nice. Next up, what do we have? We have negative log 2. There's a negative over here, so we need to distribute that in. So we have plus pi, because that's the length of the interval, logarithm of 2. And then again, double negative, that's going to be plus. We multiply this guy by pi, so that's going to be pi squared. And you'll notice one thing happens. Okay, and technically I do need to put the limit as n approaches infinity here, so I guess I'll squeeze that in. So we have minus limit as n approaches infinity of n times pi. Okay, so what is this integral going to evaluate to? That's going to be equal to, so this integral, that's going to be equal to I, and then pi squared, just pi squared, because I times pi is a constant. You multiply by the length of the interval, so it's just going to be I times pi squared, which is really quite nice because we have a negative I pi, and then you have plus I pi squared over 2, plus I pi squared over 2. So cancel, cancel, cancel. Everything is cancelling today. It's amazing. So what we're left with is, well, just the negative limit as n approaches infinity of n times pi, and then we have plus pi, and then logarithm of 2. That's amazing. Okay, so what can we conclude from this blackboard over here? We have the integral over psi 1, psi 2, and this gamma integral. What happens if we just sum all of those together? So let's put that over here. So therefore, on this blackboard at least, the integral over psi 1 plus the integral over psi 2 plus the integral over gamma, what is that going to be? Well, we have pi n minus pi epsilon, so in the limits at least. Limits as n approaches infinity and epsilon approaches 0. Well, first of all, we have the pi n, which will cancel with that pi n over there. So those don't exist anymore. And then what's going to be left? We're going to have pi log of 2. So we have pi logarithm of 2. And then we also have this negative pi times epsilon. But again, as I said before, this guy, that's going to go to 0 as epsilon approaches 0. So yeah, that's basically it. Pi log of 2 is what we get if we sum all those integrals together and take n and epsilon to infinity and so on, which is really quite nice there. All right, so let's go back to our first blackboard here. So what did we just find? The integral, these three integrals over here, what do they contribute? They contribute a pi times a logarithm of 2. That's pretty cool. This guy, that was I, so now we just have to evaluate the integrals over little gammas. As I said before, those are just going to go to 0 because you're integrating around the branch points.
And this is where my mic cut out for some weird reason. I really don't know why. But once we've shown the integrals over gamma 1 and gamma 2 go to 0 in the limits, then we're left with the final equation that is 0 is equal to I plus pi times logarithm of 2. And to solve for our original integral I, we just need to subtract pi times log of 2 from both sides, leaving us with the final result of I, our integral, being equal to negative pi times logarithm of 2. And that's basically it. Pretty cool answer, pretty cool integral, and yeah, that's basically all for the video. So I'll leave the extra part with the integral over gamma 1 and gamma 2 at the end of the video. If that interests any of you guys at all, it has the raw audio from the camera, so it really doesn't sound great without the lav mic. But that's all from me. Hope you guys have a wonderful day, and I'll see everyone again next time. Bye bye.
I guess I'll do it anyways, just to make this video feel slightly more complete. We'll just do the integral over gamma 1 because I assume the integral over gamma 2 will be pretty much the exact same. We just have a different parameterization and so on. So we'll just do a quick look at integral over gamma 1. So integral over gamma 1. How do you parameterize gamma 1? Let's do it here. So gamma 1. Notice every z can be written as, or that's going to be epsilon, and then e to the I theta, where theta, that's going to go from pi and 2 back to 0. That doesn't really matter. But then we have a dz, which is equal to pi times epsilon e to the theta d theta. So let's see what happens if we plug this in over here. We're going to get the integral of the logarithm of e to the 2 times I. Z is going to be epsilon e to the theta. Okay, then we have a negative 1, and then minus I z, once again that's epsilon e to the theta, and then we have minus the logarithm of 2, and then minus I times pi over 2, and all of this stuff, that's going to be multiplied by the differential there. That's going to be I times epsilon e to the theta to theta. And thanks to this epsilon over here, there's a few things that will be pretty much irrelevant. All of this, that's just going to vanish up to 0 because of this epsilon over here. The only thing we need to worry about, I believe, is the logarithm there. So assuming, once again, you can bring limits into the integrals once again. I couldn't really find a nice bounce. I don't know what it is with logarithm functions. You just can't find a nice upper bounce with them. If you guys know how to find an upper bounce with this, then definitely let me know. That would be amazing because I just can't figure it out. But yeah, the only thing we need to worry about is what happens if we have this epsilon and this epsilon approaching 0. Well, what's going to happen if this approaches 0? This is going to be 1, so e to the 0 is 1. We have negative 1, so we have the logarithm of 0, which is undefined. So we need to use a bit of L'Hopital's to argue this kind of goes to 0. So how do we do this? So I mean, that's really not too tricky to do over here. Let's take a look at the limit as epsilon approaches 0. The logarithm of e to the 2 by epsilon e to the theta minus 1 divided by logarithm of epsilon. So we want to write this epsilon as 1 over epsilon on the denominator, so we have infinity over infinity. So this is going to be the limit. Once again, if you differentiate the top, that's going to be something like 1 over epsilon, or e to the 2 by epsilon e to the theta, minus 1, and you have to multiply by the derivative of this guy. I mean, it's something, probably not something nice. I mean, it's something that's going to be e to the 2 by epsilon e to the theta, the derivative of the inside, and then the derivative of the inside, that's going to be 2i e to the theta, I believe. Hopefully I still remember my chain rule and whatnot. Then you differentiate the bottom over here. So that's going to be 1 over epsilon squared with a negative. So if epsilon approaches 0 here, that's not a problem. That's just going to be 1, so let's just treat this stuff as a constant. What happens if you bring this way up? So epsilon squared, that's going to be at the top now, over e to the 2 by epsilon e to the theta minus 1. This is a completeness, which is why I put it at the end. And then times some constant here, I don't know, which is that guy. And I believe for this you'll have to use L'Hopital's once again because you have 0, and if you have epsilon approaching 0, that's going to be 1 minus 1, which is 0. I mean, that's just going to be equal to the limit L of 2 epsilon over something, but then you get rid of this negative 1 here, I believe, which leaves you with 2i epsilon e to the theta times some stuff that's over here. And this is really quite nice because as epsilon approaches 0, that's 1 in the denominator, and then if there's an epsilon in the numerator, so that really does go to 0. So I mean, assuming you can bring the limits inside of the integral, which again, I'm not too sure how to find an upper bound to justify it, but assuming you can do that, then everything in here will vanish to 0. This epsilon kills off that stuff, and if you multiply the log and the epsilon here, that's going to be 0 as well, as we roughly showed over there. So, integral over gamma 2, that's going to behave the exact same way. It's an integral around the vantage points. So these two guys, that's going to contribute absolutely nothing.